Inflection points. Here we shall discuss the inflection points of a single variable in detail. First, we shall discuss the role of a second derivative in inflection points. Then we shall discuss the necessary and sufficient conditions on second derivative. Then we shall discuss the role of third derivative, and lastly we shall see, are there functions whose inflection points may be found by use of first derivative only. An inflection point is a point on graph of a continuous function at which concavity changes. Let's first discuss the concavity. A curve may be concave up or concave down. But how do we know the curve is concave up or concave down? For this, we draw the tangents at the curve or portion of the curve. If the curve lies above every tangent drawn to the curve, then the curve is said to be concave up. So, a curve is concave up if it lies above every tangent drawn on it. Similarly, if the curve is below every tangent drawn on the curve, then the curve is said to be concave down. So, a curve is concave down if it lies below every tangent drawn on it. As we know that the point of inflection is a point on curve where its concavity changes. We take two portions of curve, one is concave up, one is concave down. Let's combine them. When we combine the two portions of the curve, we get a point, this point. Note that on left of this point, curve is concave up, and on right, curve is concave down. So this point is the point where the concavity of the curve is changing. So this is called the inflection point. Here, before this point, the curve is concave up, and after this point, the curve is concave down. So this point is inflection point. Again, if we uh, take the concave up and concave down portions of the curve, and again we see that this point is the point of inflection, because on left of this point the curve is concave down, and towards right the curve is concave up. So at this point the concavity changes. So this is the point of inflection. So we can say that the point on a curve is inflection point if before the curve is concave up and after the curve is concave down, or before this point the curve is concave down and after the curve is concave up. That is, the concavity of the function or the curve changes. Now we associate a second derivative with concavity. The second derivative of a continuous function defines its concavity. If the second derivative is positive, then the curve is concave up, and if the second derivative is negative, the curve is concave down. Now we associate second derivative in finding points of inflection. We take the curves already discussed. Here we have already discussed that these 2 points are points of inflection. For first curve, before this point the curve is concave up, so the second derivative must be positive, and after this point the curve is concave down, so the second derivative must be less than 0. Now note that as this is the point of inflection. Therefore, at this point, the curve is neither concave up nor concave down. Therefore, at this point, the second derivative must be 0. Likewise, on the second curve, before this point, the curve is concave down. Therefore, the derivative must be the second derivative must be negative. And after this point, the curve is concave up, so the second derivative must be positive. But again, as this point is point of inflection, therefore here the curve will neither be concave down or concave up. So at this point, the second derivative must be 0. So we can say that to find all possible points of inflection of a function of one variable, the second derivative must be 0. So we devise a method to find the points of inflection of a curve of a single variable. For possible points of inflection of a function f of x, we shall put the second derivative equal to 0 and solve for x. Suppose we get the value x is equal to c. X is equal to c. Now, if for x less than c, f double dash x is positive, and for x greater than c, f double dash x is negative. Note that before x is equal to c, that is where x is less than c, the curve is concave up, that is its second derivative is positive, and as we move towards right of c, that is the points where x is greater than c, the second derivative is negative, that is the curve is concave down. So if we move from left of c to right of c and the concavity changes, that is the sign of second derivative changes, then x is equal to c is point of inflection. Similarly, if for x less than c, f double dash x is negative, and for x greater than c, f double dash x is positive, then again x is equal to c is point of inflection. Let's explain it. This is x is equal to c. For x less than c, the second derivative is negative, that is curve is concave down, and towards right where x is greater than c, the second derivative is positive, that is curve is concave up. Again, the concavity of the curve is changing, that is the sign of second derivative is changing from negative to positive. Therefore, x is equal to c is the point of inflection. Now we take an example to explain our methodology. We take a function f of x is equal to sine x. We find its first and second derivatives. Then we put the second derivative is equal to 0, minus sine x is equal to 0, sine x is equal to 0, and we get x is equal to 0, plus minus pi, plus minus 2 pi, plus minus 3 pi. We investigate the points of inflections for x is equal to pi and x is equal to 2 pi. Here the second derivative is equal to minus sine x. Our point is x is equal to pi. We take a point where x is less than pi, and again we shall take a point where x is greater than pi. So for x less than pi, we take x is equal to pi by 2. At x is equal to pi by 2, the second derivative is minus sine pi by 2, which is minus 1. That is, it is less than 0. And again, we take a point towards right of pi. We take x is equal to 3 pi by 2 and put it in a second derivative. f double dash 3 pi by 2 will be equal to minus sine of 3 pi by 2, and it will be equal to 1, which is positive. So at x is equal to pi, the concavity has changed. That is, the sign of derivative has been changed from negative to positive. So at x is equal to pi, we can say that the sign of second derivative has been changed from negative to positive. Therefore, x is equal to pi is a point of inflection. Similarly, we can check the same methodology for x is equal to 2 pi, and if we check, then we get x for x less than 2 pi, second derivative will be positive, and for x greater than 2 pi, second derivative will be negative. That is, the sign of second derivative has been changed from from positive to negative. So we can say that x is equal to 2 pi is a point of inflection. Let's explain it with the help of graph of sine of x. We plot the graph and label the points pi and 2 pi. At x is equal to pi, note that at x is equal to pi, before x is equal to pi, that is where x is less than pi, the curve is concave down. That is, double derivative is negative, and after pi, where x is greater than pi, curve is concave up. The double derivative is positive, as we have explained here. And for 2 pi, for the region where x is less than 2 pi, curve is concave up, and for the region where x is greater than 2 pi, the curve is concave down. That is, the derivative has been changed from positive to negative, as we have explained here. So x is equal to pi and 2 pi are points of inflection. Now we discuss the necessary and sufficient conditions on second derivative to find points of inflection. As we have already discussed by definition, if a point on a curve is inflection point, then second derivative must be 0 at that point. This is necessary condition. It says that if x is equal to c is point of inflection, then f double dash c must be 0. But the condition is not sufficient. That is, if we because a point obtained by putting second derivative equal to 0 may or may not be point of inflection. That is, if we put second derivative is equal to 0, we may get points, for example, a, b, c. Then it is quite possible that x is equal to a not a point, is not a point of inflection. And that's what we are going to discuss in our next example. We take a function f of x is equal to x raised to power 4. We find its first and second derivatives. We put the second derivative is equal to 0 and find x to be 0. Now we check whether this point x is equal to 0 is a point of inflection or not. Remember, x is equal to 0 has been obtained by putting f double dash x is equal to 0. Here, the point is x is equal to 0. In the region where x is less than 0, we take a point x is equal to 1, minus 1, and find the value of second derivative at x is equal to minus 1. It says 12 into minus 1 whole square, which will be 12, which is positive. Now we go towards right of 0, that is the region where x is greater than 0, and take a point x is equal to 1. Then the second derivative at 1 will again be positive. So the sign of second derivative has not been changed. So we say that the x is equal to 0 is not a point of inflection because the concavity has not been changed at this point, although we have obtained x is equal to 0 by putting f double dash x is equal to 0. So for x less than 0 derivative is positive, and for x greater than 0 derivative is again positive. So we can say that x is equal to 0 is not a point of inflection. Let's explain it with the help of graph of this function. The graph of this function is shown in this figure. This is y is equal to x raised to power 4. At x is equal to 0, before x is equal to 0, the curve is concave up, and after this point the curve is again concave up. That is before the second derivative is positive and after the second derivative is also positive. Hence we can say that the condition is not sufficient. Now we discuss the role of third derivative in determining points of inflection. We take the same function f of x is equal to x raised to power 4, and as we have already found that x is equal to 0 is not a point of inflection. Now we use third derivative to show that x is equal to 0 is not a point of inflection. We find the first, second and third derivatives, put the second derivative is equal to 0 and get x is equal to 0. Now at x is equal to 0, the third derivative at x is equal to 0, f triple dash 0 will be equal to 0. That is, at x is equal to 0, the f triple dash x is equal to 0. That is, there is no change in second derivative. Second derivative, no change. Since third derivative is equal to 0, it means the change in second derivative is 0. And as the change in second derivative is 0, it means that there is no change in concavity, which shows that no change in second derivative, that is no change in concavity. Therefore x is equal to 0 is not a point of inflection. So we have used the third derivative to determine whether a point is a point of inflection or not. Now again we take the function f of x is equal to sine of x, find first, second and third derivatives, put second derivative is equal to 0 and find the values of x. At x is equal to pi, we take the point pi. The triple derivative is minus cos pi, that is equal to minus into minus 1, 1, which is not equal to 0. So for x is equal to pi, the third derivative is not 0. That is, the concavity changes. We must say the second derivative changes, so the concavity changes. As the third derivative is not equal to 0, therefore there is a change in second derivative. Hence we can say that uh, x is equal to pi is a point of inflection. Here we have used third derivative to determine whether a point is point of inflection or not. Now we discuss the role of first derivative in determining points of inflection. There are certain functions whose points of inflection can be found by first derivative, and one of them is f of x is equal to x cube. We find the first derivative only and put first derivative is equal to 0 and get x is equal to 0. Now here the point is x is equal to 0, we move towards left of 0. That is the point where x is less than 0. Take x is equal to -1 and put it in second derivative. And we get f dash minus 1 is equal to 3, which is positive. That is, function is increasing in the portion where x is less than 0. Again, we go towards right of 0 and get x greater than 0 and take a point x is equal to 1 in this region. We find f dash 1. 3 into 1 whole square, that is equal to 3. Again, the first derivative is positive. That is, function is increasing. So we can say that for x less than 0, the first derivative is positive, and for x greater than 0, the first derivative is again positive. That is, the sign of first derivative has not been changed. So according to first derivative test, x is equal to 0 is a point of inflection. This point of inflection has been found by using only first derivative. Let's check its graph. And on graph, we can see that at x is equal to 0, before x is equal to 0, the curve is increasing, and after x is equal to 0, the curve is again increasing. So by first derivative test, we can say that the point x is equal to 0 is point of inflection. Now let's check our theory by using the standard second derivative definition. F double dash x will be equal to 6x. We put f double dash x is equal to 0. We get x is equal to 0. And now, before x is equal to 0, we take a point x is equal to -1 and find f double dash -1, which is negative. And now we go towards right of 0, x greater than 0. We take a point x is equal to 1 in this region. F double dash 1 is equal to 6 into 1, which is 6, which is positive. That is, the second derivative has been changed from negative to positive. That is, sign of second derivative is changed. So we can say that the sign of second derivative has been changed from negative to positive. Therefore, x is equal to 0 is a point of inflection. Now we check this by the third derivative. The third derivative is equal to 6, and we can see that at x is equal to 0, f triple dash x is equal to 6, which is not equal to 0. That is, there is a change in the concavity of a function. That is, there is a change in second derivative. So we can say that x is equal to 0 is a point of inflection. So for this function f of x is equal to x cube, we can use first derivative, second derivative, and third derivative to determine the points of inflection. Now we show that the first derivative is not enough to find the points of inflection. We must use the second derivative. We take a function f of x is equal to x cube into x minus 3. We find its first and second derivative and put first derivative is equal to 0 and get the values of x to be 0, 9 over 4. Now we draw the graph of this function. Here note that this point is a point where x is equal to 9 over 4, 2 point something. At this point, before this point, when x is less than 9 by 4, the curve is concave up. And after this point, when x is greater than 9 by 4, the curve is again concave up, that is concavity doesn't change. Therefore 9 over 4 is not a point of inflection. X is equal to 0 is a point of inflection, because when x is equal to when x is less than 0, curve is concave up. When x is greater than 0, curve is concave down. X is equal to 0 is a point of inflection. Now we use second derivative, and by putting second derivative is equal to 0, we get 0 and 3 by 2. Here, this is the point where x is equal to 3 by 2, and we note that before this point x is equal to 3 by 2, curve is concave down, and after the curve is concave up. Therefore x is equal to 3 by 2 is a point of inflection. Note that when we used the first derivative, we missed x is equal to 3 by 2. So we can say that the first derivative is not enough to find the points of inflection. One more thing, and that is uh, we draw the sine function. The point of inflection is a point where tangent to curve intersects the curve. It sounds strange, but the points of inflections are the points where tangents to curves intersect the curve.